Welcome to Calculus 1, where we'll dive into the beautiful, powerful, and sometimes mysterious world of calculus. Whether you're a high school student tackling your first calculus class, a college student looking for extra support, or an adult ready to explore math as continuing education, this course is designed for you. Calculus is often called the mathematics of change because it helps us understand how things move, grow, and interact in the world around us. From tracking the motion of planets to optimizing business decisions, calculus is the language that connects math to real life. In this course, we'll take you on a journey from the very basics, starting with limits and continuity, through derivatives and integrals, and all the way to solving differential equations using separation of variables technique. Here's how we'll break it down. First, we'll explore limits, the foundation of calculus, and use them to understand the concept of continuity. Then we'll dive into derivatives, learning how to measure rates of change and apply them to real-world problems. After that, we'll unlock the power of integration, discovering how to calculate areas, volumes, and much more. And finally, we'll bring it together in an introduction to differential equations, focusing on the separation of variables technique. I know calculus can feel intimidating, but here's the good news. You don't have to go it alone. In every lesson, I'll guide you step by step with clear explanations, practical examples, and plenty of opportunities to practice. My goal is to make calculus not just understandable, but also enjoyable. Throughout this course, you'll find practice problems, guided solutions, and helpful tips to build your confidence. And don't worry, if you ever feel the need to review a concept, you can always come back to the videos. Calculus is about more than just solving equations. It's about learning to think critically, to see patterns, and to understand the world in a whole new way. By the end of this course, you'll not only master the core concepts of calculus, but you'll also develop the tools to approach math and life with curiosity and confidence. Ready to get started? Click on the first video, and let's begin the journey together. Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button. Alright, Lecture 1, Calculus 1. Limits and continuity. So, to motivate the idea of a limit, let's consider the function f of x equals x cubed minus 1 divided by x minus 1. And I want to pose the question, what is f at 1 equal to? Well, if you simply try to substitute in x equals 1 into this function, what happens? Anybody? Is there any problems with that?
Yeah, you get 0 over 0.
Yeah, we're going to get 0 over 0, right? 0 over 0 is undefined, right? So perhaps we could, try to figure out, it must be doing something around 1, right? So we could, for example, make a table of values. So here I'll write x and f of x, and I'll just put in some values. Try it at x equals 1.25, and we would get f of x is 3.81. If we put in 1.1 for x, we would get 3.31. If I put in 1.01, I'd get 3.03. If I put in 1.001, I'd get 3.003. And then, of course, at 1, we don't know. But how about at 0.99? That's just on the left side of 1, right? We would get 2.997. At 0.9, we would get 2.97. At 0.75, we would get 2.313. We could even graph these values, and what would we see? We would see, here's x. You can see that at 1, right, when x is 0, y is at 1, so it's going to go through right here. We're interested in the point 1, and so it's going to kind of sweep through here, but we're going to have a hole right there when x is equal to 1. And if I were to look at values that are close to it, right, that correspond to values that are a little bit to the right of x equals 1, and I could also look at values a little bit less than it, corresponding to what we'd get if we had x a little bit less than 1, we can see that it looks like it's headed for 3, right?
Yeah.
So we would be tempted to say that, well, the function must be equal to 3 at that point. Well, it's not, because it's undefined. It's not x equals 1. It's not in the domain of this function, okay? But this is what motivates the idea of a limit, okay? So I could manipulate this equation a little bit more, I could do one of two things. I could recognize the difference of two cubes, because I've got x cubed here and I've got 1 cubed over here, right? Or I could do, I could say, well, this denominator is the problem. If I could get rid of that, then I would have something I could write down, right? And, well, one way to deal with problems like this is you can try to divide x minus 1 into x cubed minus 1, okay? And that's just long division using, polynomials. And I'll do that this one time. I'm not going to repeat any more long division problems, but this one is not too bad. Let me show you what you'd get. If I try to divide x minus 1 into x cubed minus 1, remember, I have to keep track of all the other terms. I've got to have 0x squared plus 0x minus 1 here on the end. And then to divide this in, I just simply look at this x cubed and I say, well, what do I have to multiply x by to get x cubed? Anybody?
X.
No, that would give me x squared. X squared. So if I put x squared up here, x squared times x is x cubed. X squared times minus 1 is minus x squared. And then I simply subtract that from this. X cubed minus x cubed is 0. And then I have 0x squared plus x squared is just x squared. Drop down the next term, plus 0x. Then I do it again. I say, well, what do I have to multiply x by to get x squared? Well, that's obviously just x. So I put plus x for this term. X times x is x squared. X times minus 1 is minus x. Then I subtract this off. 0x squared minus x squared is 0. 0x plus x is just x. Drop down the next term. And repeat. What do I have to multiply x by to get x? Just 1, right? So plus 1, 1 times x, 1 times minus 1. Subtract it off. I get a remainder of 0, so it evenly divides that. So that means that I can rewrite this numerator as x minus 1 times x squared plus x plus 1. And that, of course, is the difference of two cubes, if you happen to memorize that formula. So I can write here that this is equal to x minus 1 times x squared plus x plus 1 divided by x minus 1. And so that allows me to get rid of this x minus 1 in the denominator, right, through what I usually call the key fraction rule. If you have something in the numerator that's the same as in the denominator, they just cancel out because x minus 1 over x minus 1 is just 1, right? So these cancel out. I'm just left with x squared plus x plus 1. And so you see that we can kind of come up with this convention. I can say that the limit as x approaches 1 in this case of x cubed minus 1 over x minus 1 would be the same thing as the limit as x approaches 1 of x squared plus x plus 1, where we can now just simply substitute in 1 for each of these things. And what do we get? We get 1 squared plus 1, and that's just equal to 3. And so this notion that the value there should be 3 kind of falls out of this idea of what we're calling a limit, okay? So we can actually come up with a definition for a limit. This will be a kind of a hand-wavy definition, so an imprecise definition. Call it limit. And we'll say that the limit as x approaches c of f of x being equal to some value L means that as x approaches c, then f of x is near L. And this approaches sign, what do I mean with this approaches sign? That's kind of an important point to note. It means that it's near but different from, okay? Because in what we did just a minute ago, where we said it approached 3, well, we substituted in the value 1 into our expression, but the funny thing is that that expression would not be defined when x is equal to 1 because of the fact that we divided it out, right? Yeah. So when we had x minus 1 in the denominator, that meant that x equals 1 was not in the domain, so x cannot be equal to 1, okay? So we'll be on a little firmer ground once we have a couple of theorems that we can call on, but essentially that's what we do. If we find an expression where we can just simply substitute in the value, then that will give us the correct limit. Where we run into trouble is if we have, a division by 0 in the denominator, or it goes to infinity, something like that, okay? So these are the problems that we'll try to remedy or deal with. But this is our kind of informal definition. Okay, so let me do a simple example of a kind of a limit problem, a really easy one. Okay, so here is an example. let me see if I can find the limit as x approaches 3 of 5x minus 2. Well, in this case, it looks like it's a pretty simple matter, right? I can graph it or plot some points, but I kind of see where it's going, right? I could just plug x equals 3 into that equation, right? And what would I get? I'd get 5 times 3 minus 2, that's 15 minus 2 is 13. Okay? And so we can say that the limit as x approaches 3 is 13. Now, let me give you one to try. Yeah. So math is a discipline that really requires practice, and so there should always be an emphasis when presenting class material on making you work problems as we go along. And so this is a you try for viewers at home. You can pause the video, give this a try, come back whenever you've got it, resume, and I'll show you the solution. Anyone tell me what the answer to this is? What is the limit of 3x squared plus 12 as x approaches 2?
24.
It's 24, right? So we have 3 times 2 squared plus 12. That's just 12 plus 12. It's 24. Okay, let me give you another one. It'll be a little more challenging. How about the limit as x approaches 3 of x squared minus x minus 6 divided by x minus 3? Again, pause the video, try this on your own. All right, so this one, we could either factor the numerator, because the problem, remember, is in the denominator. I can't plug in x equals 3 because I'm dividing by 0, and that's not allowed, yes? So what I need to do instead is see if I can get rid of that denominator. And I could divide x minus 3 into x squared minus x minus 6, or I could just recognize that the numerator is, I can factor it. I can rewrite this as the limit as x approaches 3 of x plus 2 times x minus 3. I think that gives me the right answer, yeah? Divided by x minus 3, yes?
Yeah.
The x minus 3's will cancel, given that x is not allowed to be equal to 3, right? So once we do this, right, we're saying that x can't be equal to 3. Well, actually, it was always the case where x couldn't be equal to 3 because it's not in the domain, because it's undefined there. So this is now the limit as x approaches 3 of x plus 2. And that we can do. That's just 3 plus 2 is equal to 5. Yes?
Yeah.
Now, if we had graphed that, we would have seen that is where that was headed. Okay?
All right.
Now, let me do another one for you. This will show you another one of the types of the kind of the techniques that you can use to crack these kind of problems. Okay? So I'll show you one, then I'll give you one. Consider the limit as x approaches 0 of x divided by the square root of x plus 1 minus 1. So as you can see, if x is equal to 0, I get the square root of 1 is just 1, and 1 minus 1 is 0. I'm dividing by 0 again, and I've got 0 over 0, in fact, right? So what can we do to fix this up? Well, you'll see a lot of problems that are like this, and so the thing to do in this case is you can multiply by the conjugate, okay? So if I simply multiply by 1, you can always do that, right? But let me just say that I'm going to make my 1 be equal to the square root of x plus 1 divided by the square root of x plus 1, right? But let's actually carry that out. So in the top, we'll get the limit as x approaches 0 of, here I'm just going to keep it x times x plus 1 plus 1. That has to be multiplied times that, the numerator, right? And in the denominator, this times this will just give me x plus 1. Then I'll have this times positive 1 plus minus 1 times this. That just cancels it out, so we lose that square root term. And then we still have the minus 1 times 1 is going to be minus 1. And so what do we get? We get that this is equal to the limit as x approaches 0 of x times the square root of x plus 1 divided by, well, we've got x plus 1 minus 1. That's just x, right? X's will cancel. So I'm left with the limit as x approaches 0 of the square root of x plus 1. And that I can substitute in, yes? Plug in 0 here, I'll get 1 plus 1, I get the answer of 2. Follow that?
Yeah.
So just multiplied by the conjugate of this denominator here. That way I could get rid of all the square root terms down there. Yeah?
Yes.
Yeah. Let me give you one to try. Okay. Pause the video and try this one on your own. All right, so we'll use a fairly similar procedure to that. Again, we can just multiply times the conjugate of the denominator. Root of x plus 1, square root of x plus 1. Multiplying this through, I'm going to just keep one of these factors around, x versus 1, of x minus 1 times the square root of x plus 1. Just keep that, no reason to multiply that out. And the denominator, what am I going to get? I'm going to get square root of x times square root of x is just x. And then I'll get minus 1 times positive 1 is minus 1. And so you can see that I have a factor of x minus 1 in the denominator, which I can then cancel out. And I'm left with just the limit as x approaches 1 of the square root of x plus 1. And that, of course, is just equal to 1 plus 1 is 2. So the same as we had in the last problem. Okay?
Yeah.
Fairly straightforward, yes?
Yeah.
Let's look at a more challenging one. What about the limit as x approaches 0 of the sine of x over x? That one is trickier, but if you were to use a graphing utility on a calculator or on a website, for example, and type that expression in, you would see something that looks like this. Where we, of course, have a little hole right there at x equals 0, okay? Because if we plug in x equals 0, what is the sine of 0?
0.
Yeah, and what is, well, so we have 0 over 0, right? So this is undefined. Now there's a couple of ways that we can tackle a problem like this and find out what the limit is, okay? Now I'm going to show you kind of the physicist way, all right? And then later I'll show you a different way, a more mathematical way, okay? The physicist way to work on this, right, is to say, okay, well, x is approaching 0, so x is getting very, very small, right? And we know that we have something called the small angle approximation, right? So if I draw a unit circle, right, and I draw I can make a little right triangle out of that, right? So this is a unit circle, so that's 1. We'll let this be our angle x, okay? This little arc here, this is the arc S, which is just equal to r, which is 1, times x. It's the arc length, right? And if I call this distance here L, and I call this distance from here to here h for like hypotenuse, right? Then we know that the sine of theta, not theta, I usually use theta, but here we're using x, sine of x is equal to the opposite over the hypotenuse. The opposite is L, the hypotenuse is h, right?
Yeah.
And we also have this relationship that the arc length is equal to x. Are we going to need that? Not really, I guess, but kind of. You can see that as the angle gets very small, right, the arc length and this leg of the right triangle L become the same as the angle gets very, very small, yes?
Yeah.
Also, the hypotenuse, as this gets very small, gets close to 1. So what happens is the limit as x approaches 0 of the sine of x, right, is going to go towards not L over h, but instead L will be replaced by x, the arc length, and h will be replaced by 1, so that's just equal to x, okay? So you can kind of see that as that angle gets really, really small, that the sine of x approaches x, okay? That's called the small angle approximation. And if I use that here, right, I can say, well, this is approximately the limit as x approaches 0. Sine x I'll replace with x, so we get x over x. That's just equal to the limit as x approaches 0 of 1. And, well, that's just 1. And so we see that is the limit. That's what we think when we look at the graph of it. We're like, well, as you get close to 0, this function approaches 1. You can see that from the graph, yes?
Yeah.
And so here we've kind of shown it using the small angle approximation. Now let me give you one to try. Try the limit as x approaches 0 of 1 minus the cosine of x over x. And let me just point out that if you think about what the hint here is the cosine of x, as x becomes very, very small, what does the cosine of x approach in, say, the unit circle? Well, it approaches 1, right?
Yeah.
So that's the approximation to use there. So go ahead and pause the video. Try that now. Okay, so how does that work out? Well, again, if we use this approximation that the cosine of x for small x, so let's write this down, the limit as x approaches 0 of the cosine of x, well, it's not really approximate, it's equal to 1, okay? So using that in this expression here, this gives me the limit as x approaches 0 of 1 minus 1 over x, which I can rewrite as the limit as x approaches 0 of 0 divided by x, and that's just 0, okay? So in this case, it's equal to 0. Now, do limits always exist, you think?
No.
No, they do not, right? So a classic example of a limit that doesn't exist is the limit as x approaches 0 of the sine of 1 over x. Okay, and so if you punch that into a calculator or an online graphing program, what it's going to end up looking like is something like this. So this is x. We'll have okay, where these are all kind of going up to the same value here, even though they're not really drawn that way. Okay, so it's always going to be, because the sine is always in between minus 1 and 1, this will be limited to being in between minus 1 and 1, okay? And so if you look at it, it's kind of like the wavelength. Think of a sine wave as something that has a wavelength, right? The wavelength, as x gets bigger, is getting larger. So the wave is getting longer and longer and longer as you go out. As you go towards 0, though, it's getting smaller and smaller and smaller, which means that you get more and more waves per unit length as you go to a smaller interval size, right? Yeah. And so what's happening here is it's never really settling down. It's always going between minus 1 and 1. It's not approaching anything, okay? So this limit does not exist, okay?
Okay.
Let me show you another limit that doesn't exist. Let's look at the limit as x approaches pi over 2 of the tangent of x. So what does the graph of the tangent of x look like? Anyone remember? Remember, it's sine of x over cosine of x, right? And so the denominator being cosine of x, you can see where the problem is coming in, right? Every time the cosine of x is 0, you're going to be dividing by 0, yes?
Yeah.
And that's causing trouble. So if we were to graph the tangent of x, what would it look like? Well, we have, this will be, say, x. Now would this be at pi over 2? So it would be minus pi over 2. That's not enough space for the next interval. This function, if you graph it, it looks like this. Move this over. Okay, so I'm going to focus on this region right here, okay? Because you can see that if you approach it from the left, right, it's going off towards infinity, right? At pi over 2, what is the cosine of pi over 2?
0.
0. So that's where the problem is coming in, right? As you come at it from the right-hand side, though, you can see it's going off down towards minus infinity, okay? So this is a point where the limit doesn't exist. It's not headed in any place, right? It's going to depend on which side you come from. And that actually brings us to our next topic, which is one-sided limits. So if I write the limit, that's not nice looking. The limit as x approaches c, and I put a little positive sign up here in the superscript area, right? Of f of x equals L. This is called the right-hand limit, okay? And it's basically we're approaching c from the right. So if c is, say, 3, we might be approaching, we might be at 4, and then 3.5, and then 3.25, and so on and so forth, getting closer to 3, but from the right-hand side, the positive side, positive direction, you see?
Yeah.
This is a right hand limit, and then we have a left-hand limit. As x approaches c from the left. This is called the left-hand limit. Okay? So let me do an example so you see what this is all about. Consider the function f of x equals the absolute value of x over x. So here's my x-axis. This is my y-axis. And let's let this be equal to -1. And this value here will be equal to +1. And so if we graph this, right, if we choose, say, negative x values, right, the numerator will be just the absolute value of that value, right, divided by a negative number. So a positive number divided by a negative number, always negative, right? This is just -1, right? So on the left-hand side of 0, this function is always equal to -1, yes?
Yes.
And on the right-hand side, for positive x, it's always equal to +1, you see?
Yeah.
But at x equals 0, right, this is undefined. And further, the limit, as x approaches 0 from the left, that's on this, from the negative side, coming in this way, the limit as x approaches 0 from the left-hand side, the negative side of x, absolute value of x over x, is equal to -1. And from the positive side, it's equal to +1. And this brings us to a kind of an important theorem that I'm going to put right here. Let's write the theorem. The limit as x approaches c of f of x is equal to L if and only if. So the IFF, the two F's, I with two F's is a mathematical way of saying if and only if. That's like a bidirectional implication, right, if you've studied logic. If and only if the limit as x approaches c from the left of f of x is equal to the limit as x approaches c from the right of f of x. Okay? So the limit exists if the limit coming from the left and the limit coming from the right are both equal. Okay? So here the limit does not exist. There is no value that this function f of x equals absolute value of x over x approaches. As it approaches 0, there is no limit for that because it has two different values, as you can see. Now sometimes you can plug a discontinuity, okay? So if you, for example, had a function, I'll just make an easy one. If we have like a, if this is y and this is x, and we just have a line, y equals some constant value except right here, where there's a hole, right? Well, we can plug this and it will make make the limit exist because the limit will be the same from the left and the right, provided we plug the hole right there, right?
Yeah.
So that makes sense. But this whole idea, that last function we looked at, we would call that a discontinuous function, right? It's broken, and that's what discontinuous means, okay? So continuity, which is the second part of this lecture, so continuity, if, well, there's really only one thing. If the limit as x approaches c of f of x equals some value, okay? So if that limit, what does that mean? That means the limit exists, the value f of c exists, okay? And f of c is equal to L, okay?
Yeah.
If that's the case, then it's continuous. So I think we just looked at a broken function, it looked like a stair step, right? That's discontinuous. Continuous functions don't have that kind of breakage in them, okay? So the sine x over x function we looked at earlier, right? It looked like this. Something like this, right? Where we have a little hole right there. Here's x. Here's y. And we have this hole at x equals 0. If we want to fix this and make it continuous, we just have to plug that hole and add in we'll have to make a broken function. We'll say that f of x is equal to, and then we'll have sine of x over x and 1 for x equals 0. And this will be for absolute value of x greater than I'll just say not equal to 0. Okay? So it's sine x over x everywhere except at x equals 0 where it's equal to 1. Okay? Because this is called a piecewise function. And that would be continuous. Okay? Because we've plugged the hole. Now we satisfy the limit for continuity. You see?
Yeah.
Okay. All right, now I'm going to go through some fundamental theorems. These are like the main limit theorems, and I'm just going to read them off. I'll display them on the screen on the computer. But in this case, we'll let n be some positive integer, k will be some constant, f and g are functions with limits at c. Okay? So at x equals c. So the first theorem is that the limit as x approaches c of the constant k is just equal to k. Right? The second theorem is the limit as x approaches c of x is equal to c. The third theorem is the limit as x approaches c of k, constant k, times f of x is equal to the constant k times the limit as x approaches c of f of x. The fourth theorem is the limit as x approaches c of f of x plus or minus g of x is just equal to the limits of f of x plus or minus the limit of g of x. So if you add two functions together, you can break them up into two limits. Okay? Similarly, for multiplying and dividing, you can take the limit of the product is equal to the limit of the multiples, right? So the limit of f times g is the limit of f times the limit of g. With the exception that when dividing, g can't be equal to 0. The limit of f of x to the n is just equal to the limit as x approaches c of f of x raised to the n power. So whatever that limit is, raise that limit to the n power. And the same thing with square roots, right? With the caveat that f of x has to be greater than 0 when n is an even number, right? So if it's a square root or something like that, right? Because you can't have negatives in the square root. So let me just do an example problem where that might be useful. So if I take the limit as x approaches 3 of 2x to the fourth. These theorems are really what are allowing us to do the easy substitution method, okay? But the proper way to do it, of course, is to rewrite this as, well, this is equal to 2 times the limit of as x approaches 3, and then of x raised to the fourth power, right? So, and then I think it was theorem 2 said that the limit of x as x approaches c is just equal to c. So this would be equal to 2 times 3 to the fourth power, which is just equal to 2 times 81, which is just 162. Okay? So that's the proper kind of mathematical way to do it. All right? You're relying on these fundamental theorems to break this down into things that you've already, like proven, so to speak. And these are usually proven using these delta epsilon proofs that we talked about before. But given that, because these theorems exist, right, instead we can just kind of say, you know what? Instead I would just do it like this. I'd say the limit as x approaches 3 of 2x to the fourth is just equal to 2 times 3 to the fourth, which is 162. Okay? The way that I worked it up here relied specifically on the theorems, right? Breaking each of these things apart was a result of one of the theorems that I had listed just a moment ago, okay? That says I can do that. And it's all relying on this last piece right here, that the limit of x as x approaches 3 is just equal to 3. Okay, that was the second theorem that I listed. I was going to put in the squeeze theorem, but I don't think I will. It's not all that relevant for us. We really won't use it again, so I think we'll just skip over it. You can find it in any calculus book, though, and probably online somewhere. It's nothing all that deeply profound. It just basically says if you can bound a function, have something bigger than the function, something smaller than the function, and you take the limit of those two things, and their limits as you approach some value is the same, then that must be what the limit in the middle is. So you kind of squeeze in on the limits, okay? So a classic problem to work on that with is like x times sine of 1 over x. You can use the absolute value of x to kind of squeeze down where it's going, and you'll find that that limit does exist and it's 0, okay? The last thing I wanted to get to was limits of infinity and at infinity, okay? So I think we'll start with limits of infinity. And best to just look at an example. So I want to consider the limit as x approaches 0 of 1 over x. If we were to graph this, right, what does this look like? Here's x, here's f of x, 1 over x. Looks like this on this side. Looks like this on this side, okay? So I want to know what the limit as x approaches 0 is. If we look at the limit as x approaches 0 from the right-hand limit, 1 over x, what's happening as x approaches 0 from the right? What's it doing? So as I get closer and closer to 0, where is x going? Or where is f of x going?
To infinity.
Infinity, right? I'm going to denote it as plus infinity, okay? Now what if I approach it from the left? The limit as x approaches 0 from the left, 1 over x, is equal to what? What happens as I approach it from the left?
It goes to negative infinity.
Minus infinity, exactly. That's minus infinity. Okay? Now, from the previous theorem that we had, right, that said that if the limit from the left and the limit from the right are not the same, then the limit doesn't exist, then that's one reason this limit doesn't exist. In general, limits of infinity don't exist. But we do have something interesting, right? The existence of these infinities, right, is kind of the definition of what we call a vertical asymptote. And you guys have seen vertical and horizontal asymptotes in algebra. I don't recall off the top of my head how exactly we worked through those without using limits, but this is the kind of the definition of a vertical asymptote. So a vertical asymptote, if f of x approaches plus or minus infinity as x tends to c, then x equals c is a vertical asymptote. Pretty straightforward, right? So let me do an example of a vertical asymptote. This is an interesting example, I think. In physics, we have this notion kinetic energy, right? And the classical kinetic energy, we'll call it T classical, is 1/2 mass times velocity squared, yes?
Yeah.
But there's a relativistic, I'll just call it relativistic kinetic energy correction that we get right under Einstein's theory. And it says that the relativistic kinetic energy is equal to gamma minus 1 times mc squared, where gamma is equal to 1 over the square root of 1 minus v squared over c squared. And so we could, multiply through by this, and we'd get that it has two terms, mc squared divided by 1 minus v squared over c squared minus mc squared, right? And I want to ask, what's the limit as v approaches c? So the limit as v approaches c, where c is the speed of light, v is the velocity of the object, right? And that will be of mc squared over 1 minus v squared over c squared minus mc squared. So what's that equal to? Well, as v approaches c, what happens in the denominator of this first term?
It turns into 0.
Well, the whole first term does, yes. Well, v over c, or v squared over c squared, becomes 1, right, as we approach c. That gives me 1 minus 1 is 0. So I'm dividing by 0. It's blowing up this first term, making it go to infinity, right? And so this constant term makes no difference at all, okay? It's a finite constant. The limit of that is just minus mc squared. It goes to infinity. So what does this look like if I were to graph it? Where this is v, we'll let this value here be c. It means that c is a vertical asymptote, yes? And that your energy T, relative, I'll just call it T, the relativistic energy is going to encounter this vertical asymptote, which it's going to approach but never arrive at, yes?
Yeah.
The classical kinetic energy, it would have a similar shape to this, but it would be able to easily cross over this line. We'd head out like this somewhere, just keep on going forever, always getting bigger. You could have infinite kinetic energy if you wanted, right? But relativistic kinetic energy says that there's a speed limit in the universe, right? If you have a non-zero mass, right? If your mass is non-zero, then you can't go the speed of light. You see?
Yeah.
It takes an infinite amount of kinetic energy, right? You'll spend an infinite amount of kinetic energy and never arrive at c. Okay? So this vertical asymptote is the origin of the speed limit of the universe, which is the speed of light. It's kind of cool, huh? So that's limits approaching infinity. When the limit of something is equal to infinity, we'll write it down as like the limit equals infinity, but the limit technically doesn't exist, okay? It's a non-existent limit. But sometimes it's useful to know that things tend towards infinity, and so we might write that its limit is equal to infinity, but that doesn't mean the limit exists formally, okay? Now let's talk about limits at infinity. So limits, not of infinity, but at infinity. So, for example, the limit as x approaches infinity of x squared divided by x squared plus 1. Okay? So what does this look like? Well, if it wasn't for that plus 1, right, we just have x squared over x squared, and this would look like 1, right?
Yeah.
Well, if I actually graph it, this is y, this is x. Let's let this be 1, okay? What it looks like in actuality, I'm kind of getting ahead of myself here with this thing that I've drawn. If we're far away from x equals 0, right, it basically looks like 1, okay? But as we approach x equals 0, it takes on a different value, right? So how do we get this limit, though, at infinity? Well, I could, for example, factor out an x squared out of this denominator term. So let me just write that down. It'll be x squared divided by x squared times 1 plus 1 over x squared, yes? These x squareds cancel. That's the limit as x approaches infinity of 1 over 1 plus 1 over x squared, which I can then break down into the limit as x approaches infinity of 1 divided by the limit as x approaches infinity of 1 plus the limit as x approaches infinity of 1 over x squared. Yes? What does this guy do? As x approaches infinity, what does this term 1 over x squared approach? 0. So this term goes to 0, so this is just equal. The limit of x, as x approaches infinity of 1 is just 1, and then divided by the limit of x approaches infinity of 1 again is just 1. We get 1 over 1, so it's equal to 1. So the limit as x approaches infinity of this function, x squared over x squared plus 1, is equal to 1. Okay? But it gives us a chance to make a new definition, this time a horizontal asymptote. Horizontal asymptote. So y equals L is a horizontal asymptote if the limit as x approaches infinity, actually plus or minus infinity, doesn't matter, of f of x equals L. So here we see we've got a vertical asymptote, yes? Let me erase the work here. And I want to look at another example. Actually, I want you to try this example. So you try the limit as x approaches infinity. When I write infinity, I mean plus infinity, by the way, okay? Of x plus 3 divided by 5x squared minus 8. So pause the video, try that now. So the trick that we can use here is, again, I'll multiply this thing by 1, but it's a different 1. I'm going to multiply by 1 over x squared and 1 over x squared, okay? So that's going to give me the limit as x approaches infinity of, well, this term times 1 over x squared. What's it going to give me? It's going to give me x over x squared is just going to be 1 over x plus 3 over x squared. That's in the numerator. And then when I multiply this one by 1 over x squared, I'll get 5x squared over x squared is just going to be 5 minus 8 over x squared. Yes? And I'm not going to write it out again, but I can use that theorem that we had about the product and the division of f and g, right? You can break it up into the limit of the multipliers, right? So the limit of f times g is equal to the limit of f divided by the limit of g times the limit of g. And then I can break it up term by term because we had another theorem that said that the limit of f plus g is equal to the limit of f plus the limit of g, right? And if I do that, then I take the limit of this thing here is going to go 1 over x as x approaches infinity. That'll be 0, right? The limit of 3 over x squared, right, as x approaches infinity will be 0. This guy will be 5, and this guy here will be 0, right? 8 over x squared will be 0. And so we'll just end up with 0 over 5, which is, of course, 0. Let me show you one more function. This time, I'm going to use a slightly different logic. So we've seen that formally we can work this thing out algebraically, right? I can think about this. If I'm interested in the limit as x approaches infinity, that means that x is pretty big. It means that 9 is going to be pretty irrelevant, yes?
Yeah.
So this denominator is really going to be the square root of x squared, yes? And this 1, similarly, right? 7 times a really big number minus 1 is just 7 times a really big number, right? So this, as we get to big x's, right, is going to be 7x over, well, the square root of x squared is just x, right? The x's cancel, I get 7. Yeah?
Yeah.
What if I looked at it from the other side, from minus infinity? If I took the limit as x approaches minus infinity, now I'm going in the opposite direction of the same function, 7x minus 1 over the square root of x squared plus 9, right? This time, I'll still get, in the denominator, I'll get the x, because a negative number squared rooted, is still a positive number, right? But in the numerator, I'm going to get a negative x, right? So it's going to be minus 7x. The x's cancel, and I get minus 7. See that?
Yeah.
So what does this function look like? It looks like this. Here's x. Here's f of x. This will be 7. This will be minus 7. And this function looks like this. Doesn't quite cross at 0, 0 because of the minus 1 and the plus 9 in the denominator. But it does have these horizontal asymptotes at minus 7 and 7. Okay?
Okay.
So if y equals L is a horizontal asymptote if the limit as you approach either negative or plus infinity of f of x equals L. So how many horizontal asymptotes did we get here?
That's 2.
2. How many did we get in this problem we worked up here?
1.
Just 1. Of course, we've seen plenty of problems where there were no horizontal asymptotes. What's the maximum number of horizontal asymptotes you think you could get? Well, it's a good thing to go home and think about, but the answer is 2, and I think you'll convince yourself of it. That's the maximum number. What about the maximum number of vertical asymptotes? Is there a max number of vertical asymptotes?
I don't think so.
No, look at the tangent, right? The tangent of x, right, has a vertical asymptote, you know, at pi over 2, at 3 pi over 2, at 5 pi over 2, at n times pi over 2, where n is any odd integer, right? So plenty of them, infinite number of them, in fact. That's limits. It's really the first step into calculus. Next time we'll talk about the tangent line problem and the derivative.